All right, let's go ahead and take a look at example 7 from week 11. This one's going to be a little bit different than the rest. We've looked at 6 previous examples that all had to deal with quadratics and factoring. We see in this example certainly is not a quadratic. Sine of x plus cosine of x equals root 2. This is associated with our section that suggests that we should perhaps be using identities to help us solve equations. What's really tough for me here is it's hard for me to solve equations when I have two different functions that are both operating on x. It would be really nice for me here if we were only in terms of sine or only in terms of cosine. It's not directly clear what to do right here, right? So I can tell that I don't directly know how to solve right now. I know that I need to use some sort of technique. I know that this isn't quadratic, so I'm not going to use quadratic techniques. So I'm thinking to myself now, is there anywhere in our identity sheet that I see terms that look like sine of x added to cosine of x, where they have equal amounts, one of each? Unfortunately, the answer is no. There aren't any of our identities that just have a sine of a single angle added to a cosine of that same angle as an expression. We have like our sum and difference formulas. We have our sum to product and product to sum formulas, but those all involve like different quantities inside of our angles out here and just some other terms that I don't know are going to be actually helpful to us. So the thing that's tough for me here is I don't directly see what to do. It's not obvious what to do. So now I'm going to try and kind of fuzzy my look at this a little bit. I want to look back a little bit and say, well, is there anything in my formula table that looks like vaguely like this out here? When is it that we ever see sine terms added to cosine terms where they have the same input in our formula table? Well, the one that I'm thinking of, that I know of, is Euler's formula. The problem is that it has squared terms. Sine squared of x plus cosine squared of x equals 1. So the good news is that this represents sine terms and cosine terms being added together, and man, in the best possible way. Like what an awesome output that is. That's super, super simplified for me over there. That's great. On the other hand, what I see here is that these require these terms to be squared, whereas over here we don't have squared terms. But we have an equation, so it seems reasonable to me that we can manipulate this equation in any way that we want, as long as we do it evenly to both sides. So what I'm thinking here is this: the only way that I know how to rewrite any of these terms, based on what I've seen in my formula table, is this. And even this is sort of a stretch in the sense that I'm not even directly able to do this, a swap right here, because we're not quite in the right format. But if I manipulate this formula over here, then maybe I can come up with something that does have terms that look like sine squared plus cosine squared, which would then condense into a very, very, very simple 1. So let's go ahead and do that. So my first step here is going to be to square both sides. And right now, I'm going to shake my fist at you. And if you haven't looked at it in the notes, then you'd better be looking at the notes right now. Batman and Robin comic. You'd better square this thing out the right way. I'm in your home right now. I'm telling you, square this the correct way. We do not simply square each of these individual two terms. We know that whenever we square anything, a plus b squared, a binomial squared, we're always going to get the first term squared, and we're going to get the last term squared, but we're going to get 2 copies of the cross product term as well on the inside here. I need to make sure that I get an expression that looks like that over here. So I'm going to get the first term squared. I'm going to get 2 copies of the cross product term. And I'm going to get the second term squared. On the right-hand side, I'm squaring the square root of 2, which is just 2. So now, notice that one nice, let me say this differently. One nice thing happened and one not nice thing happened. The nice thing that happened is sine of x squared, cosine of x squared. We have both those two terms. It looks like these two terms underlined in blue can both join together to become 1. The bad news is we did crop up the cross product term that you can't forget. And so, with our cross product term here remaining, it looks like I have 2 sine x cosine x plus 1 equals 2, where this 1 is the sine squared plus cosine squared. From here, I'm going to go ahead and subtract 1 from both sides. And now we're in maybe a little bit better shape for solving. What I'm recognizing here now is that I still am stuck in a kind of a bummer of a situation where I have two different trig functions within my equation that I need to solve. But what I'm thinking I can do here is this. I do recognize this term here, 2 sine x cosine x. This is another one of our identities that we've seen. This is exactly 2 sine x cos x is the same thing as sine of 2x. This is our double angle formula associated with sine. So what I'm going to go ahead and do is rewrite this now as sine of 2x equals 1. So now we're actually in a really good solving shape right here. We're back into a section 7.7 solving scenario now. Now we're asking the question, what angle is going to result in a height of 1? And you should notice that we're looking for general solutions here as well. So I'm going to draw my unit circle. I'm thinking of a height of 1. And I'm going to ask myself, what angle results in a height of 1? Well, there's only one angle that's going to do that for me within 0 to 2 pi. We're looking for general solutions, so we'll state this a little bit more generally here. So it looks like our angle of 2x, the angle here is not just x, the angle is 2x. Our goal is to solve for x. The angle that we are applying the sine function to is 2x. So our angle is equal to pi halves. And what I know is that I'm actually going to get more than just that, right? We can take an additional lap around. We can take an additional lap around. Any additional 2 pi that we add on will still leave us coterminal with that same angle, and therefore it should also give us that height of 1 that we require to make this statement true. Finally, to solve for x, I'm going to go ahead and divide both sides by 2. So this seems like this should be our general solution to this problem. But there's a huge but right here. We actually have a little bit of work left to do. The thing that we saw in the notes is that a move that's very, very dicey in general is this right here. When we square both sides of an equation, we lose information about whether the information that we squared was positive or negative. You should recognize that if I square the number 3, I get 9. If I square negative 3, I also get 9. Well, if I'm asking you then the question, hey, what number did I square to get 9? You're not sure. It could be 3 or negative 3. The squaring has washed away that sign information, the positive negative information. So what I'm worried it might have happened here is this. When we squared both sides, we lost some information about the signage, the positive negative sign that might be associated with some of our solutions. So when we find our final solutions, it might be the case that some of these aren't actually supposed to be associated with our original equation. Maybe some of these are supposed to be associated with the negative case when we're only interested in the positive case, or vice versa. The bottom line is, I'm not sure that I can trust that all of these solutions are actually going to work. The reason I know that I can't trust it is because one of our algebra steps in our solving process was squaring both sides. Anytime that you square both sides of an equation as an algebra step, you might have introduced extraneous solutions, so you have to check your answers anytime that you square both sides as one of your algebra steps. In other cases, we can trust that what we solved for is what we were looking for and we're good, but in the cases where we square both sides, we've lost positive negative information, so we might have introduced solutions that work for one route but don't work for the other route. So what we need to do right now is say, really? All those? Is that actually all of our solutions right there? So let's go ahead and check some answers here and see what we see. And by the way, as I'm erasing right here, I'll say, I actually did this problem wrong. In the PDF that's posted online, I stopped right here with my solution when really what I should have done is I should have stopped and checked my solutions. I forgot to do this check even myself, which is why I'm really shaking my fist at you right now. If you do squaring on both sides as an algebraic step, you have to check your solutions. That's the rule that we're setting up here. So what I'm thinking to myself is, let's just try a bunch of these. This represents an infinite number of solutions. Let's plug some of these guys in here and see what we get. If I'm going to start listing some of these, by the way, let's just list a couple. The first positive solution is pi fourths. We then could do an additional pi units of rotation, also known as 4 pi fourths. That's going to get me to 5 pi fourths. And in general here, I'm just adding 4 pi fourths over and over again. So I'll get 9 pi fourths, and I'll get 13 pi fourths, and on and on and on, right? Infinite number of them out there, but that's sort of what they look like at first. So let's start trying some of these. Let's check a solution here. Let's see what happens if we do use the value of pi fourths. Is this really a solution? I'm going to plug it in. So what I'd like to know is this correct? Maybe I'll indicate this here with a question mark. Well, I know the sine and the cosine of pi fourths. Those are both going to be root 2 over 2. And what I know about adding 2 copies of root 2 over 2 is that the 2 and the 2 are going to cancel and leave me with root 2. So yes, it looks like we've confirmed that pi fourths is in fact one of our solutions right here. I'm sure that pi fourths works. I solved for it. I plugged it back in. Everything worked out like it was supposed to. Pi fourths is definitely one of our solutions here. Let's check the next one. What I think I'd like to do also in this case, by the way, is think about where each of these solutions live. I'm going to get rid of my old unit circle here for a minute. What have we found when we did this guy right here? So I'm going to reassociate this with a new unit circle here. Well, our solutions that we found are the ones that are located at pi fourths, which is there. We've also found the ones where we add pi from there, so add 180 degrees. So those are the other solutions that we've found. So it looks like all of the solutions that we've found to this equation live at either this location or this location here. This is both going to help us out with identifying our trig values here, as well as understanding why we're going to get the final solution that we're going to get here. So this is sort of my picture referencing the location of each of my solutions now, each of my individual just x solutions, not my 2x, which is what my previous unit circle was associated with. When I do 5 pi fourths, I'm going to check my solution by plugging it in. Sine of 5 pi fourths plus cosine of 5 pi fourths. And we're asking the question, is this the same thing as root 2? Well, we can go ahead and evaluate it. And the thing that's going to help me evaluate it, by the way, is this picture. This picture is reminding me that 5 pi fourths lives in the third quadrant. It is one of my pi fourths, so I do think I'm going to get root 2 over 2 stuff, but I can see that it's to the left, so the cosines are negative. It's also down, so the sines are going to be negative. So here I'm going to get negative root 2 over 2. I'm going to get another negative root 2 over 2. And we're asking the question, is this equal to root 2? Well, it looks like we've got two groups of negative root 2 over 2. And so when my 2 and 2 cancel, it looks like what we were left with is negative root 2. And therefore, it looks like we actually got this guy wrong. We were hunting for the output of positive root 2, and we got negative root 2 on the left side when we plugged that stuff in. So it doesn't look like 5 pi fourths should actually be one of our solutions here. It looks like it's close. Notice it's only off by a negative, and that's exactly what we said we should expect to happen here. When we square both sides of the equation, as we did in our first step, squaring causes you to lose positive negative information. And so what happened here is we ended up creating some solutions that were almost correct. They were just off by that missing piece of positive negative information that we had washed away by our squaring process out here. So it's always the case that your extraneous solutions will seem super, super close to being right. They're just always off by a sign. And when I say a sign, I mean a positive negative, not like a sine and cosine out there. So which of my solutions should I trust? Well, I know that pi fourths lives in the first quadrant. It's always going to give me things, excuse me, let me come back real quick. I know that things like pi fourths and 9 pi fourths, which is coterminal with the same angle right here, right? It's just an extra 2 pi around. I know that these ones are always going to land in quadrant 1. Quadrant 1 is always going to give me positive values for root 2 over 2. Those are always going to combine to give me positive root 2 like I want. What I can also see here is all of the other solutions that live in quadrant 3. They are all going to give me negative root 2 on the left, which is not going to work out. So it seems like things like 13 pi fourths can also be discarded here for the exact same reason. 13 pi fourths also lands at that location right there. It is coterminal with 5 pi fourths. So what I found originally for my solution was pi fourths plus just pi k. But what I'm now seeing is that I really actually want to go straight from pi fourths to 9 pi fourths. Notice that this is a jump of 8 pi fourths, and 8 pi fourths is 2 pi. So it actually seems like we're going to skip every other solution. Every other solution here was extraneous, and so it actually seems like what we want to state our final solution then as is we do want to start counting from the pi fourths term, but it looks like we're going to go every pi, or excuse me, instead of going every 1 pi, we're going to go every 2 pi to get to our next answer here. So plus 2 pi k. So as my final statement here, in the homework, I had stated this is the final correct answer because I hadn't checked for my extraneous solutions and removed every other one. In general, we should have had a 2 pi k, but we should have divided 2 pi k divided by 2 to get the 1 pi k. Once we list and check our solutions, we realize that all of the ones that landed in quadrant 3 were actually extraneous solutions. They were false solutions that we came up with. We really only wanted to keep the true solutions, which ended up being the ones that corresponded only with the positive pi fourths and all angles that are coterminal with it. So we went from pi fourths to taking an extra lap to get to the next pi fourths. That's an additional 2 pi k right here. So you should have solved to here first. But then our check of our, for extraneous solutions, we removed half of all of them and landed at this as our new general form for our solution here.